there's a rate at which radioactive decay occurs. And that rate, or we can quantify that rate by using something called the half-life. The half-life, which we'll represent as T sub 1/2, is the amount of time it takes for an exponential decay to reach half of its original value. And we can apply this half-life to radioactive decay. So this equation here represents exponential decay of radioactivity. We've got N. N is our number of nuclei at some time t, and that equals the N sub 0, which is our number of original nuclei that we started with before the radioactive decay process occurs, times e to the minus lambda t. And in this case, well, t is time, but lambda is not the wavelength here. In this equation, lambda is something that we call the decay constant. Lambda is defined as the natural log of 2 divided by the half-life. Remember, we represent the half-life as T sub 1/2. Now here's an example of a exponentially decreasing decay. It's a radioactive decay process. Here's our number of nuclides. We start out at some maximum value at T is equal to 0. And then the radioactive decay occurs and our parent particle decays into a daughter particle. And so we're decaying here, 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 following this equation. Here's a chart that represents all of our data points that were plotted here. N is our number of nuclides after some time t. Remember, a lot of those nuclides are going to be decaying. So N is the number of those original nuclides that are still remaining. So after one half-life, half of those original nuclides are remaining. And then at twice the half-life, let's see, we had 50,000 remaining at one half-life. So at twice the half-life, there's going to be half of that 50,000 that remains. And then at 3 times the half-life, there's going to be half of those 250,000 that remain, and so on down the line. When a source is highly radioactive, this means that the number of decays per unit time is very high. So we can define what we call the activity, or capital R, to be the rate of decay in a radioactive process, expressed in decays per unit time. So R is equal to delta N over delta T. Delta N is the number of decays that occur per unit time, or per length of time. The SI unit for activity is given the name becquerel after Henry Becquerel. 1 becquerel is equal to 1 decay per second. The Curie unit for activity is defined to be the activity of 1 gram of radium. So 1 Curie, which we represent as Ci, equals 3.7 times 10 to the 10 becquerel. And this is named for Marie Curie. Her picture is right here. And she was very important in the early studies of radioactivity. She studied in particular radium. The unit of Curie here was named in her honor based on the activity of 1 gram of radium. And she also won 2 Nobel Prizes, 1 in physics and 1 in chemistry for her studies of radioactive processes. We're going to think about this idea of half-life in order to date the age of an artifact. In particular, we're going to think about the Shroud of Turin. So some people claim that this artifact called the Shroud of Turin, which we see an image of that here, is the burial shroud in which Jesus was wrapped after the crucifixion. And they used a process called carbon-14 dating, which relies on these radioactive decay processes in order to find the actual age of the Shroud of Turin, to see, could this Shroud of Turin have actually been the burial shroud of Jesus? We're going to find out yes or no. we're going to calculate the age of the Shroud of Turin, given that the amount of carbon-14 found in the Shroud of Turin is 92% of that in living tissue. Now, carbon-14 is interesting because, well, there are 3 naturally occurring isotopes of carbon. You've got carbon-12, which is 12, it's got 6 neutrons and 6 protons. It's the most stable isotope of carbon. 99% of 99% of all the carbon is carbon-12. About 1% of carbon is carbon-13, and a trace amount of carbon is carbon-14, which is the subject here. All living organisms have some ratio of carbon-14 to carbon-12 within them. When organisms die, they no longer absorb carbon-14. Therefore, it's possible to determine the age of a material by measuring its activity per unit mass as a result of the decay of carbon-14. So we're going to think about, the amount of carbon-14 that was left in the Shroud of Turin at the time period when it was measured, in order to determine whether or not the shroud could be as old as Jesus. To calculate the age of the Shroud of Turin, we're going to start with the relationship between the original number of nuclei present, which is n sub naught here, and the number n of those nuclei remaining at a later time. So the number of nuclei remaining equals the original number of nuclei times e to the minus lambda over t. So our unknown is t, that's what we're trying to solve for. And our knowns, as we were told, that the amount of carbon-14 found in the shroud is 92% of that in living tissue. So it's 92% at some later time t compared to what would be present at time t is equal to 0. So that tells me that n over n naught, this relationship n over n naught, is equal to 92% or 0.92. Okay, writing that as a decimal. And well, let's see. We have this quantity lambda, which is our decay constant. Lambda is equal to the natural log of 2 divided by the half-life of our nuclei. In this case, we have carbon-14. The half-life of carbon-14 is 5,730 years. So now, using this information, we need to solve for our unknown, the age of the Shroud of Turin. So we have to take this equation and we have to do some algebra to solve it for our t. We can divide both sides by n sub naught here. Then n over n sub naught is equal to e to the minus lambda t. Okay, so we've done this a few times before. How do we get rid of the e to the stuff, e to the exponent on both sides? Well, we can take the natural log of both sides, because remember that the natural log of e, let's say to the n, gives us back just n. Okay, so if I take the natural log of both sides, I will find that the natural log of n over n naught is equal to the natural log of e to the minus lambda t. So that's the natural log of n over n naught is equal to minus lambda t. So I'm going to get back all the stuff that was in that exponent. Then I divide both sides by minus lambda. So then my time that I'm looking for, t, which will tell me the age of my shroud, is equal to, I'll put the minus sign on top, minus the natural log of n over n naught divided by our decay constant lambda. Okay, now let's see. I'm kind of running out of room here. So I'm going to move us up here. So T is equal to minus the natural log of my ratio n over n naught, my ratio of the amount of carbon-14 at some time t, which is when this measurement was being taken, divided by the original amount of carbon-14. We know there's 92% left of the original carbon-14. So n over n naught here is going to be 0.92. And then we're going to divide it by our decay constant, lambda, which will be natural log of 2 divided by our half-life of carbon-14, 5,730 years. Okay, so this is going to equal, well, you'll take the natural log of 0.92. The natural log of 0.92, actually the natural log of any number less than 1 is going to give you a negative number. You're going to have negative times a negative that will give you a positive. So you're going to take minus the natural log of 0.92, that will give us a positive number, divide it by the natural log of 2 divided by 5,730. That gives us a time of 689 years. So using the amount of carbon-14 left in this shroud and the half-life of carbon-14, we know that the Shroud of Turin is 686 years old. And we think that Jesus's death happened around 2,000 years ago. And that's telling us that this shroud is more than 1,000 years too young to have been used during Jesus's crucifixion. They use carbon-14 dating in order to date rocks, in order to date fossils as well, to date mummies too.